In this chapter, we're going to look at an example of calculating uncertainty, and we're going to look at the uncertainty for a 1 kilogram mass. We saw previously, in a previous chapter, that the standard uncertainty for a mass was 0.044 milligrams, and we divide by 3 based on the NIST assurance program, which suggests that the 0.044 is for 3 sigma. So now we have a standard uncertainty of 0.0147 milligrams, and that's a number that we've found from the previous work in an earlier chapter. The number 3 is because this says it's a 3 sigma value, and I want to get back to a single standard deviation for all of the uncertainty calculations. And before 1994, we could choose a value 2 or 3, but now we're using the number 3 based on the NIST recommendations. We're also going to look at the standard deviation of the process, and we're going to take that by looking at the average value coming from a control chart. And let's assume that in this case, the standard deviation of the process turned out to be 0.03341 milligrams. This is actually being taken from an experiment which we do not have the full details for in these notes, and so I can't show you where that came from, but it is actually just the standard deviation of the X bar for the control. So using the standard uncertainty differences now, we are recommended by NIST to do this, which is to take the average from the lab minus the average from the NIST standard for the standard and divide by √3. That √3 is very comparable to the √3 we used for when we looked at the scale resolution. So putting the numbers in, we can now find the uncertainty, the standard uncertainty, due to the difference between the control chart average and the expected value from the NIST is 5.375 micrograms, or 5.375 times 10 to the minus 3 milligrams. We're now going to look at several other uncertainties, and as with all uncertainty types of calculations, we try to look at each uncertainty separately, and then we'll combine them all later on. When we're doing a mass calibration, one of the concerns that we have to worry about is the buoyancy, and that is because the mass is in air, and we're really measuring its weight, and its weight is a combination of its true weight less the buoyancy due to the displaced air. And so what we have to look at now is also how much the density of the air changes, because that affects the buoyancy. So let's say that we've got these numbers from the process. The temperature is being controlled within 0.1 of a degree centigrade. We can measure the pressure, or it does not change by more than 0.1 of a millimeter of mercury, and the humidity is known within about 1%. Most labs will try to control the humidity, and so we can know it reasonably accurately. Remember, all of these 3 parameters, temperature, atmospheric pressure, and humidity, all contribute towards the density of air. And so we're looking at here saying the temperature could change from 20 to 20.1. It's actually a plus or minus, which is looking one-sided here. Similarly, the pressure, one-sided, and the humidity, one-sided. So let's look at the density. This is a standard equation we gave you before, or you can use online research tools and such like. But essentially, if we know the temperature of the air, and we know the humidity of the air, and the pressure of the air, it's possible to calculate the density. So this equation at the top is to calculate the density. The numbers here, E is not actually 2.71, it's 2.7, can't remember the numbers, but it's the natural E, number E. And we can either calculate this one or look it up in tables. But essentially what we're doing now is we've got ready to calculate the density of air. And what we're going to do in this case, it's a little bit like a perturbation technique. We're going to say, let us find the density when all the parameters are at one extreme and compare them to the middle. So we've got the 2 temperatures. We've called them initial, we've called them final. It doesn't really matter whether we say the middle and the biggest, but essentially we've decided to call them initial, final. So there's the middle value and the largest, the middle for the pressure and the largest, and the middle and the largest. largest for the humidity. If you're following these numbers through, remember that here in this equation, T for temperature is actually in degrees centigrade, and we need to add the absolute zero because the equation relies on absolute Kelvin measured from absolute zero. So putting the numbers in before, here in the initial or the meal value are all the pressures and humidities for the and temperatures for that. Here they are for the final. And so when we calculate the densities and find the difference between them, here is the delta PA, delta rho A. This is the potential change in density due to the temperature, humidity, and atmospheric pressure uncertainty. And we see here it is 0.00039 milligrams per cubic centimeter. That is the standard uncertainty because the others are all done at 1 uncertainty. So now let's look at the actual buoyancy force. The actual buoyancy force is going to depend on the difference in densities between the air density and the density of the item and the change in the difference in volumes. So let's look at the density of the unknown and of the standard. The density of our unknown mass, we're going to assume is something like 7.84 grams per centimeter cube. Remember, this is taken from the experiment, and this number is likely to be the biggest, as we mentioned here, the worst case situation for this particular experiment. So we don't have the numbers in our book to show you, but those are based on the uncertainty, the measurements of the unknown. The density of the standard is assumed to be 8, again from documentation. So now we can find that essentially that relates back to an uncertainty in volume for this 1 kilogram mass of 2.55 centimeters cubed. One thing I want you to notice at this stage is that I have way more significant figures than we would normally expect. That is very common in uncertainty analysis, is to keep the number of significant figures to be very large and then round off at the very, very end, because you're never quite sure when these are going to be important or not. So don't round off numbers too early, keep them to full significance, and then round off at the very end. Of course, if you're doing calculations in a spreadsheet or something, that will automatically happen. So now I've got a potential change in volume, an uncertainty in volume. I've got an uncertainty in density, and so I can calculate my buoyancy force as density times volume. Recall that we have to be careful to get the units right all the way through, so track carefully on the units. That now is going to be called U sub 01, and that is the uncertainty in the measurement due to air density, temperature and pressure, and humidity uncertainty. We also need to find the uncertainty due to the unknown density of the unknown mass. So we saw before that we have a slight discrepancy potentially in volumes, and so now, due to the density differences, and so now we can calculate the density times volume calculation for that as well, and we end up with this 1.19 milligrams per cubic centimeter. And in this particular case, what we're going to assume is that this has been taken by going to the Cal Lab and averaging all of the measurements, similar measurements taken in the lab. So again, we don't have the numbers to show you, but this is a typical kind of number that would come out. So this now is heading towards the error in assuming the volume of the weights is due mainly to the error made in the error made in assuming the volume of weights is due mainly to the error in assessing the density of those weights. So again, recognizing density is mass over volume and rearranging the volume, since we know that, and we can come up with the second correction in density, and that is 0.00557595, again to too many significant figures, and that is our standard uncertainty because we do not know the density of the unknown mass as well as we may like to know it. So now we come to the NIST method of applying an uncertainty surveillance. We're looking at the control chart, and And what we do is a root sum of the squares of all of the standard uncertainties. We're multiplying by 3. That's essentially putting us at 99% for our surveillance limit. And we now look at the numbers. Here they go. These are the ones we calculated earlier in this chapter. We do a RSS, a root sum of the squares calculation, and we get the total uncertainty now for the surveillance limit is 0.11 of a milligram. Now, we now compare that to the uncertainty due to the difference in the measured quantities, x bar minus the NIST value for the standard mass. And if we look at that, since our difference is less than the surveillance limits, and also the standard uncertainty for the difference is less than US, and that's one standard deviation because they are standard uncertainties. Since both of those are accepted, then we can say that our calibration is basically successful. Now let's look at combining the uncertainties to find the final uncertainty. We need to combine the type A and type B separately, but it turns out that since it's a root sum of the squares calculation, we can actually put them all into one calculation. If I do not need to assess those type A and type B separately, I'll do it in one big go. And if I want to separately assess the type A's and type B's, I'll calculate these separately. Putting the numbers in that we've just pulled out in the previous few slides, we find now that the square root of the sum of the squares is 0.03732,682. Again, right now quoted too much accuracy. This is now the combined standard uncertainty. Let us expand it by using a k-factor. I'm chosen a k-factor of 2 representing 95% confidence. I know that it's 1.96, but we use 2 as our coverage or k-factor. Multiply by 2, and using the traditional expansion equation rather than the latest versions, we now add in this bias, this consistent error. This consistent error we calculated in a previous chapter. It was 0.05 milligrams. So I combine that in, and I now have a total uncertainty at 95%. At 99%, sorry, because I've now included a factor of 3, out of 0.15 milligrams. So from 0.07 at 95, full expansion using a k-factor of 3 now, we end up with 0.15 milligrams as our total 99% uncertainty. So 2 questions we may want to ask when we're considering uncertainty. And the questions are basically this one: which distribution and confidence level should we choose when we estimate the uncertainty? Or alternatively, how large or small should the magnitude be? Let's look at the 2 approaches we can use. One is to work forwards from all of the parameters that we measured. We then use the methods we've just shown and calculate the final uncertainty. Or the other one is to start at the end and say we need a certain amount of uncertainty, or not more than a certain amount of uncertainty, and we work backwards and find the equipment that will match that method. So in method 1, where we go forward, it's based on basically on the system that's there. It's based on all the science and the physics and the phenomena that happened, and we do quantitative evaluation as we move forward. And we're going to use all of the equipment that's been defined, and eventually we're going to come up with the final uncertainty. So after we've found those, we do a statistical analysis, just what we've seen, of the measurement process. We calculate the standard deviations and draw the control charts, all in the forward domain from the basic science. And then finally we calculate the uncertainty of the measurement. But the concern is that we may end up with either too small an uncertainty that we can't obtain required for the process. We have to take into all sorts of other issues. For example, we may want to consider the ratio between the required tolerances and the uncertainty. That's something some industries like to know. We need to know the limits of technology, and there may be some legal or other issues going on as well, which the forward method, at the end of the day, we can decide if we've met them, but it doesn't help us choose. The other one is to start at the end and work backwards, and then we'll look at the uncertainties that come out. Let's look at an example. Let's assume that medical experts have told us that plus or minus 3 degrees Fahrenheit is the maximum temperature for the human core body without it causing potential injury or death. So our requirement, looking forwards, is that we must measure within plus or minus 3 degrees Fahrenheit. And we're going to say, let's have a 10 times factor on this because it's a potentially life-threatening situation. As a consequence, we're going to be measuring trying to measure much more accurately than something with a 3 degree Fahrenheit thermometer. So we've decided that we have a thermometer that looks like it might match that has a accuracy of 0.1, or at least a 0.1 degree Fahrenheit readability. The actual uncertainty is a little more than that. We decide to take a series of measurements using that to check it out. We find the standard deviation from the control chart. Remember, this is just a fictitious one, not a real example at this stage. And we find that the standard deviation of the values is 0.05 degrees Fahrenheit. It's arbitrarily assumed. We found it from our pretend experiment. We want the uncertainty from that, and we calculate that to be 0.08 degrees Fahrenheit. And so we conclude that, yep, this is going to give us the accuracy we need, but it's going to be a very expensive type of solution. And so let's look at, we've got 6 degrees plus or minus 3 degrees is our maximal range. We found that our uncertainty for the experiment was 0.08. And so the tolerance we're being allowed is 3. Our uncertainty is 0.08. And we've found a factor of 37.5. Our measurement system is therefore 37 times more accurate, if you like. I hate to put a number on accuracy, but essentially it's 37% times more accurate than we actually need. Typically, we want to work at a ratio of about 4 to 1, most industries. We've got equipment that's too expensive. Here's the block diagram of what we've done. The tolerance, the specification is plus or minus 3 degrees. We defined how we're going to measure. We picked a thermometer. We looked at the statistical process control, the flow chart, the control chart. We calculated the uncertainty. And we found that for the chosen thermometer, we ended up with an accuracy ratio of 37.5. And that conclusion was, yes, it's going to do the job, but it's probably not cost effective. So let's look at the other approach, which is to say, let's start off at the other end and say we've got a readability of 1 degree Fahrenheit on our thermometer now. At the next grade down, in which we get an uncertainty of about 0.9, standard uncertainty of about 0.9. We are going to pick 2 different accuracy ratios. We'll pick a 10 to the 1, just like before, because it's a critical process. And we'll find, therefore, the uncertainty is going to be 9 degrees Fahrenheit. We come to the conclusion that 9 degrees Fahrenheit could be fatal, and therefore we'll see what happens when we pick a ratio of 4 to 1. 4 times 0.9 is 3.6, and it's not exactly 3, but it's close. So here's the flow chart of what we've done for the second method. We chose a thermometer this time with a readability of 1 degree Fahrenheit. We assumed 10 and found that we couldn't meet the tolerance. We assumed an accuracy ratio of 4, which is more typical. And we found that we got within 4 degrees, and we decided that that is probably acceptable. We would then have to do the statistical process control to confirm the